If you're watching this lecture video Tuesday and you haven't yet voted, please pause this video and go vote. I would much rather you do that today than finish this lecture video. Please, 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 please remember to vote. If it's not Tuesday, keep playing. I don't know. Don't pause the video, just watch this and have an awesome lecture. But if it is Tuesday and you haven't yet done it, pause the video, get in your car and go vote. Dope. Have a good one. What's up, everybody? Welcome to the 18th lecture of Trig. Today we're going to be finishing up the last little bit of section 3.3 and maybe get into a little bit of 3.4. So to begin with, I thought we'd review what we know so far about vectors. The first thing we know is that a vector has magnitude and direction. After that, we know that we can rewrite vectors in component forms. We know how to apply scalar multiplication and vector addition. From there, we know how to calculate the magnitude of a vector. We know how we can represent vectors geometrically. So let's say we wanted to add two vectors, or we wanted to apply scalar multiplication or something of that sort. We know how to geometrically represent it. And we know that two vectors are said to be equivalent if they have the same magnitude in the same direction. Now, question. If I went through and wanted to add, subtract, multiply, do all of this, that, and the other with vectors, what are those properties going to look like? How are they going to behave? Let's look at that. So really quickly going through all of the properties of scalar multiplication and vector addition, what we've got here is, starting off, the commutative property, where u plus v is going to be equal to v plus w. Both u and v are vectors. For the second property, we have the additive identity, where this is actually supposed to be the zero vector. And the zero vector is just a vector whose components are all equal to 0. This is again called the additive identity, because it doesn't matter what the vector u is. Anytime you add it to the vector 0, you're going to get back u. Here we've got the associative property. We've got the additive inverse property. We have the commutative scalar multiplication property. I'm sorry, I meant to say the associative scalar multiplication property. We have distribution of scalar addition across multiplication with some vector u. Here we've got another distribution property. We have the multiplicative identity, and then the zero property. So multiply a vector by 0, you get back 0. And now for these last two, these are the two I really wanted to talk about. Let's say we've got a vector v, we multiply it by some scalar c. The norm, or the magnitude of c times v, is going to be equal to the absolute value of c times the magnitude of v. That's convenient. So if we have a vector with magnitude 5, and we multiply it by, say, some scalar 2, then to find the magnitude of that new vector, we would just take the absolute value of 2 times 5. We'd say, all right, it's 10. Then we have another thing. It's not really a property of vectors, but I wanted to group it in with all of these just because I thought it was a good time to introduce it. What we've got here is the unit vector u of v. So what's a unit vector? A unit vector is a vector that points in the same direction as your original vector, that has a magnitude of 1. Notice what we've got here is v, the vector v, times 1 over the magnitude of v. So we can think of this as a scalar, right? And if we do that, let's set some random number, just a number, equal to 1 over the magnitude of v. Okay, if that's the case, then k times v, the magnitude of k times v is going to be equal to the absolute value of k times the magnitude of v, but k is equal to 1 over the magnitude of v times the magnitude of v. This is all just going to come out to be 1. So just as a quick explanation or proof of why this is true, what we've got, through this operation is a new vector, in this case we're calling it u, that points in the same direction as the original vector, but has only a magnitude of 1. And we'll see that in just a second. Having said that, do remember that when finding the magnitude of a vector, you want to apply this formula. That's what these double bars mean. It's sometimes called taking the norm of your vector. So actually a very, 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 can't stress it enough, very important observation object in math. Having said that, let's move on. Why did I do that? I don't know. All right, so for this first example, what we want to do is we want to find the unit vector of v, and then we want to graph both the unit vector and v together on the same graph. All right. First thing we want to do then is going to be to find u, right? To find the unit vector. Before we can do that though, we've got to find out what the magnitude of v is. Because remember, the unit vector is usually written with u just because of convenience. But we could write it as whatever we want. But remember, the unit vector is going to be the vector v divided by its magnitude. So we need to find that magnitude first. Okay. So the magnitude of v is going to be the square root of -2 squared plus 5 squared. This is going to come out to be square root of 29 So, what we've got then, once we apply all of this, is that u is equal to 1 over the square root of 29 times the vector v. Well, this is going to be equal to 1 over the square root of 29 times the components -2, 5. And what this is going to come out to be then is -2 over the square root of 29 times 5 over the square root of 29. Okay, so we want to graph these now, right? So to graph these, let's first graph V, because it'll be the easiest thing to graph, I think, since these numbers are messy. To graph V, we want to go to the left -2 positions and up 5 positions, 5 units. So over, this will be about 1 unit, 2 units, and then up 1, 2, 3, 4, and 5. So we're going to be about here-ish. About there-ish. So 29 is pretty close to 25. So square root of 29 is going to be 5 point something. -2 divided by something close to 5 is going to be about 0.4. So that's going to be somewhere over here-ish. Now, same thing here. Well, that's going to be about here-ish, right? So, our unit vector is going to be this vector right here. Notice it fell on our line, like exactly on our line. That's convenient. And if we were to measure it, it'd be about 1 unit compared to the rest of the length of this. So this is generally what we're going to be doing with things like the unit vector and the magnitude, finding the magnitude of vectors. Having said that, there's more. I know, aren't you excited? I am. This is so awesome. Let's look at what else is left. Now, before I get into this next problem, there's a question of the week. What does the back of my lab coat say? Also, having said that, I want you to, so that people don't just copy answers from each other, I want you to write the difference between the month you were born and the day you were born. So I was born February 26th. My answer would be whatever the back of my lab coat says, 2 minus 26 is -24. So back of my shirt, -24. Anyhow, question of the week, like I said. Getting back on track though, mathematicians and physicists oftentimes like to use what's called standard unit vectors. And the reason why we like to use them is because it makes the math look like something we're more used to. It's just friendlier notation sometimes. And what standard unit vectors are these two vectors. There's actually several different unit vectors that we can use, but in 2 dimensions, we have just I and J. Fun fact, in 3 dimensions, it's IJK, and I am not kidding about that. It's actually IJK. Yeah, getting back to this. So in 2 dimensions, the standard unit vectors are the vector 1, 0, represented with I hat, and the vector 0, 1, represented with J hat. Now, I say mathematicians and physicists like to use these a lot, and because they're convenient notation sometimes. But why is that? Like, how could this be convenient? What am I talking about? How do they use this? Let me show you. Show you by answering this question. We want to rewrite the vector u using I and j. So how might we do that? The first thing we might do is to write out u in component form. U in component form is u1, comma, u2. But we can expand this out, right? We could break it up into 2 different vectors added together. this could be rewritten as the vector u1, comma 0 plus the vector 0, comma u2. Now the vector u1, comma 0, this can be rewritten as u1 times the vector 1, 0. The vector 0, u2 can be rewritten as u2 times 0, comma 1. So we've got this going on. But 1, 0, that's I. And 0, 1, that's j hat. So I can rewrite this as u1 times I hat plus u2 times j hat. This looks like something we're used to, right? Now let's play with this. Let's use this notation in a couple different problems. See how it behaves, see what we get. Now, I haven't talked about adding vectors together in this form. So before we do anything else, let's put it back into component form, add them together, and then play with these to see what we have to do to add these together. Okay, so to start off with, putting u back into component form, we know u is going to be -3, comma 8. And we know v is going to be 2, comma 1. So adding u and v together, is going to be equal to -3 plus 2, comma 8 plus 1. That's going to come out to be -1, comma 9. Okay, well, that took some work because we had to put it back into component form and then add. Wouldn't it be nice if we could just add these together and not have to worry about putting it into component form? Well, we could absolutely do that. And to show you that, let's play with it. So we had u plus v, where u is the vector -3 I hat plus 8 j hat plus v is the vector 2 I hat plus 1 j hat. So we're going to drop the parentheses and combine like terms. So to do that, it's going to come out to be -3 I hat plus 2 I hat plus 8 j hat plus 1 j hat we can pull out the I and the J's now. And we can just do the basic addition now. This is going to come out to be -1 I hat plus 9 j hat. which is exactly what we said it was. So it adds the normal way, exactly like how we're used to. We've got like terms, we pull them out. Those like terms have a meaning. We know how to use that meaning. And we can start working with it a little bit more easily, like I said. Okay. So what else do I have? What else might we do with this stuff? Well, from here, one thing we might do, one thing I might ask is, given a vector in this form, what's the magnitude of that vector? Well, here we can look at it and say, all right, that's the square root of -1 squared plus 9 squared. So the square root of 82. Okay, cool, that was quick and easy. And to find the unit vector, just multiply it by a scalar. So we could treat it the same way we would this. Pretty straightforward, actually. Yeah, let's keep charging ahead. So I want you all to think back to the beginning of the semester. Beginning of the semester, we talked about what's called the unit circle. And we said the unit circle is a circle that's traced out by the edge of a line with radius 1. And that any point x, y on that circle can be written, the coordinates x, y can be written using cosine theta and sine theta. Now, I want you to think about vectors. Let's say we've got a vector v from the origin all the way up to here. Now we have, or we know, that every vector has attached to it a unit vector. We already talked about it, right? Unit vector. It's just the original vector divided by its magnitude. Well, the nice property of all unit vectors is that they have a magnitude of 1. So that means they have a length of 1. And if they have a length of 1, then that must mean they're parallel. They sit along one of these lines, right? One of these radii. That what I'm saying is, must mean we can embed it inside of a circle of radius 1. Which must mean that I don't have to write my unit vectors in terms of v. If I wanted to, I could rewrite my unit vectors in terms of theta. So we can rewrite our unit vector to be equal to cosine theta sine theta. And if we wanted to get back to v, all we have to do now is multiply by the magnitude of v, and we'll get back v, assuming we know theta. To show that, let's look back at what the unit vector is. The unit vector u is equal to v divided by the magnitude of v, multiplying both sides by the magnitude of v, we get that the magnitude of v times the unit vector is equal to our original vector v. So if we know the magnitude of v, and we know the angle of direction, so if we know this angle then all we need to do is take cosine theta sine theta, this vector, and multiply it by the magnitude of v. Okay, but what if we just have v? What if what we know is just this? How can we get theta back? Well, to get theta back, we could just take the ratio of the two. Now let me show you what I mean. To get theta back, and let me clarify too, because there's some details I need to add into this. So, because v is equal to the magnitude of v times the unit vector, which is equal to the magnitude of v times cosine theta sine theta if we wanted to solve for theta, we could take tangent theta, right? Well, that's really equal to sine theta over cosine theta. But if we multiply this by the magnitude of v divided by the magnitude of v, then what we're going to have is that this is equal to v2 over v1, right? Because this negative 3,5 is equal to v1 comma v2, which is equal to the magnitude of v times cosine of theta, comma, the magnitude of v times sine of theta so by taking v2 and dividing v1 and dividing it by v1, we can set tangent equal to that, apply our arctangent, and find theta. Now, I know my explanation of all of this might be a little confusing. I'm throwing a lot at y'all today. If you look at the notes in 3.3, there is an example that's just called direction angles that explains it in a slightly different way that might jive better with some of y'all. So please look at that and spend some time thinking about this. This is not going to come easy to y'all, or to all of y'all anyhow, most of y'all. This is going to take some time to think about. It's not the easiest thing in the world, and it does take a second to actually understand. So, stop, rewind, rewatch, read the notes. And then, if that doesn't help, come talk to me, please, by all means. I'm always available to y'all. But do take a couple minutes, take more than a couple minutes. Take some time to understand this. Because this is the big thing. This is kind of the crescendo of the class right here. Cool. Let's keep moving forward. All right. So for this example, we want to rewrite both of those vectors in terms of their directional angle. So that means we want to find what cosine theta, sine theta are. We need to find theta, and we need to find the magnitude of our vectors. That's a lot, but not too much. To start off with, we've got the vector u is 3i plus 3j. The vector u is equal to 3i plus 3j. We know that that means the tangent of theta is going to be equal to 3 divided by 3. Well, that's just equal to 1. Okay, so automatically, that must mean then that theta is equal to 45 degrees. This chalk is killing my allergies. Well, if that's the case, then all that's left is finding out what the magnitude of u is, right? Well, the magnitude of u is going to be equal to the square root of 3 squared plus 3 squared which is equal to the square root of 18, which if we wanted to, we could rewrite as 3 times the square root of 2. Okay. Well, now together with all of this, what we've got is the vector u is equal to the magnitude of u times sine or cosine theta sine theta. This is because of everything we just did just a minute ago. Well, we know what theta is, we know what the magnitude of u is, so we can put all this together now. This is going to come out to be 3 times the square root of 2 times cosine of 45 degrees, comma, sine of 45 degrees. From here, if we wanted to check to make sure that this is in fact the values that we claim it to be, we could go up back, calculate what cosine of 45 is, calculate what the sine of 45 and the cosine of 45 are, then multiply by our scalar and check to see if what we get is the same thing as what we started with. So let's do that really quick. Well, we know that the cosine of 45 degrees is equal to square root of 2 over 2, and we know that the sine of 45 degrees is also equal to the square root of 2 over 2, so 3 times the square root of 2 times our vector cosine of 45 degrees, comma, sine of 45 degrees is going to come out to be 3 times the square root of 2 times the vector square root of 2 over 2, comma, square root of 2 over 2. To make this easy on ourselves, let's first just multiply the square root of 2 through. When we do that, we're going to get that this all comes out to be 3 times 2 over 2, comma, 2 over 2, which is equal to 3 times the vector 1, comma 1, or the vector 3, comma 3. Once we multiply that 3 all the way through. Dope. So we did in fact get our original vector, right? Absolutely, because this is equal to 3i hat plus 3j hat. For the record, in case you're wondering why I keep calling that I hat, j hat, it's because whenever you put this triangle thing over top, it's called a hat. I don't know why. I honestly don't. But I hat, j hat, cool. Just separates it from a normal I or a normal j so that the reader knows what they're looking at as a vector. We use the hat when we're writing it. When we're typing it, we would make this bold. So in the book, you'll see these I hats and j hats as just bold I's and bold j's. But when we're writing it, we should denote it with a hat. Anyhow, yeah, so we just showed that what we got here was in fact equal to our original vector u. So for the vector v, it's going to be about the same, right? Just going to take the tangent of 3 over negative 4, of negative 4 over 3. We're just going to work it all the way through. Same way. So let's look at that. So in the case of vector v, things get a little wishy-washy here, but only because of how our tangent behaves, and I'll explain that in just a second. But first, we know, just because the vector v has the components 3, negative 4, we know that the tangent of theta is going to be equal to negative 4 over 3. So to solve for theta, we want to apply the arctangent, right? Well, the arctangent gives us approximately negative 53.13 degrees. Okay, this is where things get a little dicey. It's negative degrees, right? So that means we've moved down from the positive x-axis. Moving this way. Well, what we want is the direction angle. That's the angle moving counterclockwise from the positive x-axis. So it's this angle here labeled in the orange. What that means then is that what we want to do is we want to add 360 to our angle negative 53.13 degrees. And when we do that, we're going to find that this angle in orange is theta. It is 306.87 degrees. Okay, so we've got the direction angle. It means we can start playing with the sine and cosine now, right? Also means that all that's left is going to be finding the magnitude. Well, our components are 3 and negative 4. So we move over to the right 3 and we move down negative 4. So finding the magnitude here is just going to be straightforward. 3 squared plus negative 4, the quantity squared, I'm going to take the square root of all of that. Well, that's going to be 9 plus 16, but 9 plus 16, that's 25, so it's the square root of 9 plus 16, which gives us the square root of 25. Well, the square root of 25 is 5. This is one of those times where it does come out to be a nice round number. But because the square root of 25 is 5, that means the magnitude of v is just 5. Like I said, this is one of those few times where it does come out to be a nice round number. That doesn't happen hardly ever. But neither here nor there. So because we have the magnitude of v now, we can find out what v is in terms of our direction angle. We can now rewrite it in those terms. And when we do, we're going to find that v is equal to 5 times cosine of 306.87 degrees, comma sine 306.87 degrees. Now I want you all to notice something for just a second here. What we've got when we rewrite all of this part here, well, it's going to be equal to v1 over the amplitude of v. This part here, it's going to be equal to v2 over the amplitude of v. We said this whole thing was v, or this 5 is equal to the magnitude of v of, the magnitude of v. So what we really have here is this cosine of the direction angle, sine of the direction angle, it's equal to the unit vector of v. That's all it is. So we could go the other way and have found the magnitude and divided our vector by that. There's a couple different ways we could have gone. So to show what I mean, we could have, instead of going about it this way, we already know what the square, or what the magnitude of 5 is, so we don't need to find it this time. But keep in mind in the future we would. So working forward, you'll see what I mean in just a second. Things get a little bit different. So we want to find the unit vector for v. This is going to be 1 over 5 times 3 comma negative 4, which is going to be equal to 0.6. Actually, let me just write it as a fraction. 3 over 5, negative 4 over 5. So v would be equal to 5 times 3 over 5, negative 4 over 5, which should be equal to our cosine and sine here. So we could have found this in another way, and then found cosine, and then found sine, should we want the direction angle. The point of what I'm trying to say here is the unit vector will always be equal to this sine and cosine vector. Always. Assuming you found the correct directional angle. So one way to check whether or not you have your correct directional angle is to go ahead and calculate what your sine and cosine are, and to compare it to the unit vector calculated this way. That's one way. So having said that, that is all I've got for y'all today. So I'll let y'all go. Have a good one, guys.